at point A. Okay. So if I'm going to remove the support now, okay, we're going to draw our free body diagram. Right. So like what I told you guys, like RA is pushing, okay, or AY is pushing that direction, right? And we know that RB is going in this direction. And this is 576.923 times 10 to the power 3 Newton. Remember what I taught you guys earlier in class, right? If we have not done this calculation, you can assume that this is coming down, up, pushing outwards, right? If the beam is pushing inwards on its own, then it's going to do what? Its own compression, yes or no, right? Sorry, yeah. If the beam cannot push itself inwards, okay? So this assumption we make regarding our free body diagram can be changed, right? Remember earlier what we taught over here? Remember we taught over here, right? We're going to assume both to be what? Pushing itself what? Outwards. Likewise, over here, you can also assume them to be pushing outwards. Down here, I cancel it because after our analysis, we realized the 576.923 is acting what? Upwards, right? So now we want to find what is our AY, okay? So from here, we can finally use our what? Static analysis. All right, we finally going to use our static analysis. So based on the transformation, so this is X, Y, rotation about Z, right? So now we can have positive that is going up, summation about forces in the Y direction is equal to 0. So we will have AY minus by 300 times 10 to the power 3 minus by 600. Hold on, 300 times 10 to the power 3 minus by 600 times 10 to the power 3 plus by 576.923 times 10 to the power 3 is equal to 0. So therefore, AY will be equal to 900 minus by 576.923 is 323.077 times 10 to the power 3 Newton. Okay, times 10 to the power 3 Newton. Okay, straightforward. Okay, nothing special. There's no special ingredient, is there? There's no, right? There's no special ingredient. It's like Kung Fu Panda, the soup, yeah? No special ingredient. It's just very simple stuff. Now,
Sir, I have a quick question.
yep.
So earlier you said if you go up a little bit.
Yep.
So earlier we discussed that the 576 Newton load, it exists only when we don't have the K and D loads, right?
So when you are analyzed, so you're talking about this stage, right?
Correct.
Right. So at this stage, when they are pushing back RB, you don't need to analyze the 600 and 300 again, because you've done it earlier already. You've done it here already.
Okay.
Does that make sense? So over here, the first step, when you remove the load support at B, you consider the 300 and 600, right? Done already. You cannot consider your load twice, okay? Then from here, okay, the next one, when you look at RB, right? When you look at RB, you focus on RB now. You don't need to consider D and K anymore because it's done in step 1 already, okay? So you don't need to analyze your structure twice. Does that make sense?
Yep.
Okay.
Okay.
Okay. Right. So we are going to look at, so this is this is pretty straightforward. Okay. So next I'm going to look at something very similar, but the loading is a bit different. So let's look at example number 1. Okay, so we're going to take this diagram. So as I said, I've given this question on Avenue. I hope before you come to class, you just open them. Okay. Right. So we have a composite bar. Okay, so we have a composite bar, consists of a 20 millimeters A36 steel, AB. Right. So AB is made of steel. Right. Then DA, then 50 meters red brass at DA and CB. So this is brass. And the next one is also brass. Okay. So we are going to find the average normal stress in each section due to the applied load. Okay, we're going to look at each section due to the applied load. Okay, so this question over here is not any different than what we have done before. The only thing you have to be careful is we have to be careful in how you want to remove, or where you want to remove your load. Okay, where you want to remove your load. So what I will do first, so we are going to draw our free body diagram first. I'm going to start with a free body diagram first. Okay, we're going to start from our free body diagram. So we're going to start from free body diagram. But before we go on, I will highlight the Young's modulus. Okay, so E of brass is equal to, for this case, 101 gigapascal. And the E of steel, okay, so E of steel, I'm going to do 200 times, or 200 gigapascal. Okay, so in fact, we can also calculate. Okay, so the area of AB, so it's going to pi. So the diameter is 20, radius will be 10. Okay, squared. So this will be equal to pi times 0.01 squared. So it's equal to 314.159 times 10 to the power minus 6. And then area of DA and area of CB, they're the same because they have the same diameter. So it's 50 millimeters. So the radius will be 25. Okay, so 0.025 squared times by shift pi. So it's equal to 1.963 635 times 10 to the power minus 3 meters squared. Okay. So the first thing we're going to do, we're going to draw our free body diagram. So if we were to construct our free body diagram, right? X, Y, okay. So we have our member. Okay, so we have one section like this. Whenever I do drawing, there's something wrong. Interesting. Okay. Okay, so this is our brass section. Then this is our steel, right? So we're going to divide this into 3 sections again. Okay, so this is our point D. This is our point A. Then we have our point B. And then we have point C. Like what we have mentioned, this is our brass, steel, brass. Okay. And then we have a load acting over here. All right, we have a load acting down here. So we make it one load because it's 75, it's 150 kilonewton, right? And then the other load is going the other way. It's at 200 kilonewton. Okay, right. So we are going to assume that our loads are going to be acting in this direction, right? That is our reaction or dx, and this will be our dy. Okay, right. So we also realize that the structure, okay, from here we know that from here we can see that the structure is statically indeterminate, right? So when that's the case, we have to apply what? Delta L plus by delta R must be equal to 0 to solve this problem. Okay, it's statically indeterminate. Okay, so from here we know that we are going to divide so step 1 again. Just step 1. We're going to remove the support, right? The support at dy. Okay, we're going to remove the support at dy, right? So what I'm going to do now, right? So it looks confusing down here. Okay, so if I remove the load at dy, I'm going to remove the support at C. Sorry, not D, at point C. Okay, I'm going to remove the support at C. And now it looks a bit confusing. So if I remove the load at C, will A, B, C the 150 and the 200? Will A, B, C the 150 and 200? Will the B, C, C the 150 or 200? Yes or no? It gets a bit confusing. So what I usually tend to do, okay, I'll copy the whole diagram. Okay, I will paste. And then what I tend to do is I'm going to rotate right by 90 degrees. So when I rotate by 90 degrees, you can see better, yes or no? So now the support is still there, yes or no? Right? The support is at D. And then at point C, you're allowed to stretch. Okay, so we are going to calculate, right? We're going to calculate over here what is our delta L, right? So you can, I mean, I can see this better now. I can see the hangman theory better now. Yes or no? Right? So this will be my section 1, section 2, and then my section what? 3. So we are doing step 1, remove the support at C. Okay, so I think I labeled this wrongly. This should be CY. Right? I think I also labeled this wrongly. Okay. So this will be our CY. Do apologize. Or CX. Okay. Okay, not Cy. So from here, okay, we are going to look at deflection. Okay, so